Sound is a fascinating and complex phenomenon that involves the transmission of vibrations through a medium, such as air, water, or solids. Here's a detailed explanation of what sound is. Sound as a physical concept. Sound is a mechanical disturbance from a state of equilibrium that propagates through an elastic material medium 1. It is an acoustic wave that consists of alternating compress ions and rarefactions, which are regions of high and low pressure, respectively 1. These waves are generated when an object vibrates, causing the surrounding medium to vibrate as well. Types of sound waves. There are two basic types of waves, transverse and longitudinal. Sound waves in air and other fluids are longitudinal waves, where the particles of the medium move parallel to the direction of wave propagation 1. In contrast, transverse waves, such as those on a stretched string, have particle motion perpendicular to the direction of wave propagation. Properties of sound waves. Frequency, the number of times the wave oscillates per second, measured in Hz, Hz. Wavelength, the distance between two consecutive points in phase on the wave, such as two compress ions or rarefactions. Amplitude, the maximum displacement of particles from their equilibrium position, which relates to the loudness of the sound. Speed, the rate at which the wave travels through the medium. The speed of sound varies depending on the medium and its temperature. Perception of sound. In human physiology, sound is the reception of such waves and their perception by the brain too. The audible range for humans is typically between 20 Hz and 20 kHz, which corresponds to wavelengths from 17 meters to 1.7 centimeters in air at atmospheric pressure 2. Sounds outside this range are known as ultrasound, above 20 kHz, and infrasound, below 20 Hz, which are not audible to humans but can be perceived by other animals or detected by special equipment. Applications of sound. Sound has numerous applications in various fields, including music, communication, medicine, ultrasound imaging, engineering, acoustic materials, and navigation, sonar. In summary, sound is an essential part of our lives, allowing us to communicate, enjoy music, and interact with our environment. It's a physical phenomenon that can be scientifically analyzed and has practical applications across many areas of human activity. Sound travels through different mediums by causing the particles within those mediums to vibrate and transfer energy from one particle to another. The way sound travels through a medium depends on the medium's properties, such as its density, elasticity, and temperature. Here's how sound travels through the three primary states of matter. Solids. In solids, particles are tightly packed together, which allows sound waves to travel quickly through the material. The vibrations caused by sound waves are passed from particle to particle through direct contact. This is why sound can travel through solids much faster than through liquids or gases. For example, if you tap on one end of a metal rod, the sound will reach the other end almost instantaneously because the particles in the solid metal transmit the vibrations efficiently. 1. Liquids. Sound also travels through liquids, but the particles are not as tightly packed as in solids. The vibrations caused by sound waves move through the liquid by pushing the particles closer together, compression, and then pulling them apart, rarefaction. While sound still travels quickly through liquids, it is slower than in solids because the particles have more space to move around and are less rigidly connected. 1. Gases. In gases, such as air, the particles are much further apart compared to solids and liquids. Sound waves traveling through a gas cause the particles to bump into each other, transferring the vibration through the medium. However, because the particles are so spread out, the sound travels slower in gases than in solids or liquids. The speed of sound in dry air at room temperature is approximately 343 meters per second. 1. Factors affecting sound propagation. Density. The denser the medium, the faster sound can travel through it, as the particles are closer together. Elasticity. A medium's ability to return to its original shape after being disturbed also affects sound speed. The more elastic the medium, the faster sound will travel. Temperature. Generally, the warmer the medium, the faster sound will travel because the particles move more quickly and can transfer the vibrations more rapidly. Overall, sound needs a medium to travel, and it cannot move through a vacuum because there are no particles to transmit the vibrations. This is why there is no sound in space. Certainly, an echo is a sound that is reflected off a surface and heard again by the original source of the sound after a delay. 1. Here's how echoes work. Creation of sound waves. When you make a sound, the air, or any other medium through which the sound is traveling, vibrates. These vibrations create sound waves that travel away from the source. Reflection of sound waves. If these sound waves hit a flat and hard surface, like a wall or a mountain, they bounce back towards the source. This is similar to how a rubber ball bounces back when thrown against a hard surface. Perception of echoes. For the reflected sound to be perceived as an echo, there must be a sufficient distance between the sound source and the reflecting surface. This allows enough time for the sound to return and be heard as a distinct repetition of the original sound. If the reflected sound arrives too quickly, in less than about 0.1 seconds, the human ear cannot distinguish it from the original sound, and it is perceived as a reverberation rather than an echo too. Conditions for clear echoes. The reflecting surface should be large and flat. There should be minimal absorption of the sound by the medium or other objects before it reaches the reflecting surface. The distance between the source and the reflecting surface should be at least 17 meters to allow a clear distinction between the original sound and the echo too. Echoes in nature and technology. Echoes are commonly experienced in nature, in places like canyons or valleys, where sound waves can travel long distances without much obstruction and then reflect off large rock faces. In technology, the principle of echoes is used in devices like sonar and radar, where sound or radio waves are emitted and their reflections are used to detect objects or navigate. In summary, echoes occur when sound waves are reflected back to the source from a large, flat surface, and they are heard as a separate sound due to the time delay in their return. Sound localization is the process by which humans and other animals determine the location of a sound source. It involves several auditory cues that our ears and brain use to pinpoint the direction and distance of sounds. Here's a breakdown of how it works. Interaural time difference, ITD. This refers to the difference in the time it takes for a sound to reach each ear. If a sound comes from the right, it will reach the right ear slightly before the left ear. The brain uses this timing difference to determine the direction of the sound source. 1. Interaural level difference, ILD, also known as interaural intensity difference. This is the difference in the sound pressure level reaching each ear. A sound coming from one side will be louder at the closer ear and softer at the farther ear due to the head shadow effect. The brain uses this level difference to help localize the sound source. 1. Pinna effect. The outer part of the ear, called the pinna, helps to filter and modify sound waves depending on their direction. This helps the brain to determine the vertical location of the sound, whether it's coming from above, below, or at ear level. 2. Head-related transfer function, HRTF. This describes how sound waves are affected by the listener's head, ears, and body. It provides additional spatial cues for sound localization and is unique to each individual. 1. Duplex theory. This theory combines ITD and ILD to explain how we localize sounds. ITD is primarily used for low-frequency sounds, while ILD is used for high-frequency sounds. The brain integrates these two types of information to form a complete picture of where a sound is coming from. 1. Neural processing. The auditory system processes these cues through complex neural pathways. Neurons in the superior olivary complex of the brainstem are involved in calculating ITDs, while other neural circuits are sensitive to ILDs. The auditory cortex then interprets these signals to create a spatial map of sound sources. 1. In summary, sound localization is a sophisticated process that relies on a combination of auditory cues and neural mechanisms. It allows us to navigate our environment more effectively and react to sounds from different directions. Binaural recording is a method of recording sound that uses two microphones, arranged with the intent to create a 3D stereo sound sensation for the listener of actually being in the room with the performers or instruments. This effect is often created using a technique known as dummy head recording, where a mannequin head is fitted with a microphone in each ear. Binaural recordings are intended for replay using headphones and will not translate properly over stereo speakers. 1. The term binaural literally means having or relating to two ears. Binaural recording techniques take advantage of the natural spacing and shape of human ears to capture sound in a way that mimics human hearing. By doing so, it can create an immersive audio experience that gives the impression of three-dimensional space. Here's a more detailed look at how binaural recording works. Dummy head recording. A common method for binaural recording involves using a dummy head with microphones placed in the ears. The head is designed to simulate the average human head and ear shape, capturing sound just as a person would hear it. Natural ear spacing and head shadow. The microphones are spaced apart to match the average distance between human ears, and the dummy head creates a head shadow, which affects how sound is heard by each ear, contributing to the 3D effect. Playback through headphones. For the full effect, binaural recordings should be listened to with headphones. This ensures that each ear receives only the sound intended for it, without the crosstalk that occurs with speakers. Binaural recording is different from standard stereo recording, which doesn't factor in the natural ear spacing or the head shadow effect. While stereo recordings can give a sense of left and right, binaural recordings can also provide a sense of depth and height, offering a more realistic audio experience. Certainly, The Haas effect, also known as the precedence effect, is a psychoacoustic phenomenon that plays a crucial role in our perception of sound. It was first described by Dr. Helmut Haas in 1949. Here's an explanation of how it works. When two identical sounds are played in quick succession, with a slight time delay between them, our brain perceives them as a single sound coming from the direction of the first sound. This is because the brain prioritizes the first sound it hears, which is known as the preceding sound, and uses its direction to localize the sound source 1. The time delay between the preceding sound and the following sound is critical for the Haas effect to occur. If the delay is less than approximately 30 milliseconds (ms), the listener perceives the sounds as originating from the direction of the first sound. However, if the delay exceeds 30 ms, the listener may start to perceive the second sound as an echo or a separate sound source 1. Impact on audio perception. The Haas effect has a significant impact on audio perception, especially in stereo recordings and sound reinforcement systems. Audio engineers use this effect to create a sense of width and spaciousness in recordings. By introducing a slight delay to one of the stereo channels, they can manipulate the perceived localization of sound, making it seem wider than the physical separation of the speakers 1. Applications. In music production, the Haas effect can be used to enhance the stereo image of a mix, giving it a more immersive and live feel. In live sound reinforcement, the Haas effect helps to improve sound localization and intelligibility by time-aligning speakers and using delay speakers strategically. In conclusion, the Haas effect is a powerful tool in audio engineering that leverage our natural sound localization mechanisms to enhance the listening experience. Reverb, short for reverberation, significantly affects our perception of sound by adding depth, spaciousness, and realism to audio recordings. Here's how reverb influences sound perception: depth and distance. By varying the amount of reverb, you can create a perception of depth and distance in your mix. Sounds with less reverb will seem closer and more upfront, while sounds with heavy reverb will appear farther away, as if they are deep within the sonic space 1. Natural ambience. Reverb adds a natural ambience that emulates singing or playing an instrument in a particular space, such as a room or concert hall. This makes the sound feel more live and authentic too. Enhancing musical elements. When applied to instruments like guitars or vocals, reverb can significantly alter their tone and character. It can make the guitar sound as if it's played in a large hall or a tight room, depending on the type of reverb used too. Decay time. The decay time of reverb determines how long a reverberation persists after the original sound stops. A longer decay time creates a more spacious effect, while a shorter decay time keeps the sound tighter and more focused too. Early reflect ions. The early reflect ions phase of reverb consists of the first echoes reaching the listener. These help the listener subconsciously judge the size of the space and are more distinguishable than the later, overlapping echoes that characterize the reverberation itself. 3. Transforming the sound of music production. Reverb has transformed music production by allowing sound engineers to recreate spaces artificially. This adds space and dimension to records, making them feel more immersive. 3. In essence, reverb shapes the characteristics of recordings by simulating the way sound behaves in different environments. It's an essential tool for creating professional and captivating soundscapes in music production. Music is an art form that involves organizing sounds in time to produce a composition that includes elements of harmony, melody, rhythm, and color. It's a cultural universal found in every human society and serves as a means of expression, communication, and artistic enjoyment. Here's a detailed explanation of what music is. Fundamental elements of music. Rhythm. This is the pattern of sounds and silences in time. Rhythm gives music its structure and helps to convey the tempo and groove. Melody. A sequence of notes that are perceived as a single entity. It's often the most recognizable part of a song or piece of music. Harmony. The combination of simultaneously sounded musical notes to produce chords and chord progressions. Harmony supports the melody and adds richness to the composition. Timbre, also known as tone color, it is the quality of a musical note or sound that distinguishes different types of sound production, such as voices and musical instruments. Dynamics, the variation in loudness between notes or phrases. Dynamics contribute to the emotional expression of music. Cultural and emotional aspects. Music transcends language and culture, allowing people to express complex emotions and ideas. It can evoke a wide range of responses, from joy to sorrow, and can be used to communicate where words fail. Music is deeply embedded in many social activities, religious rituals, and significant life events, Creation and performance. The creation of music can involve composition, improvisation, and performance. Musicians use various instruments, including the human voice, to perform music, which can range from carefully composed pieces to spontaneous improvisations. Genres and styles. There are countless music genres and styles, each with its own traditions and innovations. These can include classical, jazz, rock, pop, electronic, folk, and many others. Each genre has its own set of rules and conventions, but there's also a lot of crossover and fusion between styles. Music and technology. Advancements in technology have transformed how music is created, distributed, and consumed. From the invention of musical instruments to recording technology and digital streaming, these changes have made music more accessible to a wider audience. Music industry. The music industry encompasses a range of professionals, including songwriters, performers, sound engineers, producers, and others who work together to create, perform, and distribute music. In essence, music is a complex and multifaceted art form that plays a vital role in human culture and society. It's a form of expression that can be both deeply personal and universally understood. The mathematics of music is a rich and fascinating subject that explores the deep connections between musical theory and mathematical concepts. Here's a detailed explanation. Frequency and pitch. The most fundamental connection between music and mathematics lies in the concept of frequency. The pitch of a note is determined by the frequency of the sound wave, which is measured in Hz, Hz. The higher the frequency, the higher the pitch. For example, the standard concert pitch A4 is tuned to 448 Z1 intervals and ratios. Musical intervals, which are the differences in pitch between two notes, can be expressed as ratios of frequencies. Simple ratios correspond to consonant sounds. For instance, the octave 2-1, perfect fifth 3:2, and perfect fourth 4:3 are intervals with simple frequency ratios that sound harmonious to the ear. 1. Scales and tuning systems. Different cultures have developed various scales and tuning systems based on mathematical principles. The well-known Western chromatic scale divides the octave into 12 equal parts, called semitones, using a geometric progression. This equal temperament tuning system allows for the easy transposition of keys but slightly alters the pure intervals found in just intonation, which uses whole number ratios too. Rhythm and meter. Mathematics also plays a role in the rhythmic aspect of music. Rhythms are patterns of sound durations, and they can be described using mathematical proportions and sequences. Meter in music refers to the regular grouping of beats, which can be analyzed using numbers and patterns too. Harmonic series. The harmonic series is a sequence of frequencies that are integer multiples of a fundamental frequency. This series is the basis for the concept of overtones or harmonics in music, which are higher pitches that resonate with the fundamental pitch and contribute to the timbre of a sound too. Mathematical structures in composition. Composers have used mathematical structures to organize music. For example, the Fibonacci sequence and the golden ratio have been employed to structure compositions, creating a balance between predictability and surprise too. Set theory and serialism. In the 20th century, composers like Arnold Schoenberg developed serialism, which uses set theory to organize pitches. This approach treats all pitches as part of a set and applies mathematical operations such as inversion and retrograde to manipulate the set too. Mathematical analysis of music. Music theorists use mathematics to analyze and understand the structure of music. This includes studying patterns, symmetries, and transformations within a piece of music, which can reveal deeper insights into its composition and performance too. In summary, the mathematics of music encompasses a wide range of topics from the physics of sound to the abstract structures used in composition. It's a field that demonstrates the beautiful interplay between the arts and sciences, showing how mathematical principles can manifest in the creative expression of music. The Pythagorean tuning system is a method of musical tuning based on the mathematical ratio of 3:2, which represents the frequency relationship of a pure perfect fifth. This system is named after the ancient Greek philosopher Pythagoras, who is often credited with its discovery, although the system's origins may date back to Mesopotamia. 1. Here are some key points about the Pythagorean tuning system. Perfect fifths. The system constructs scales using a series of perfect fifths, each tuned to the ratio of 3:2. Starting from a single note, tuning subsequent notes a perfect fifth apart creates a sequence that can be used to derive a scale. 1. Consonance and dissonance. While the perfect fifths in Pythagorean tuning are very consonant, other intervals, such as the major third, can sound dissonant because they do not conform to the simple integer ratios that characterize just intonation. 1. Pythagorean scale, any scale constructed from pure perfect fifths 3:2 and octaves 2:1, is considered a Pythagorean scale. In ancient Greek music, this system was used to tune tetrachords, which were then combined to form scales spanning an octave 1. Extended versus 12-tone temperament. Extended Pythagorean tuning corresponds directly with Western music notation without a limit to the number of fifths. However, in a 12-tone Pythagorean temperament, one is limited to 12 tones per octave, which can lead to issues like the Wolf fifth, a dissonant interval that arises due to the cumulative effect of tuning in pure fifths 1. Historical usage. The Pythagorean tuning system was widely used by musicians up to the beginning of the 16th century. It was ideal for its pure fifths, but the out-of-tune nature of other intervals led to the development of other tuning systems, such as equal temperament 1. In summary, the Pythagorean tuning system is a historically significant tuning method that uses the pure perfect fifth as its foundation. It has influenced the development of Western music theory and practice, despite its limitations in handling certain musical intervals. That was all. Goodbye.